The second speaker this morning is Nicola Kovenski, and he will tell us about heavy light correlators at the end of the worksheet.
Okay, so thanks to the organizers for the opportunity to talk here and for putting together this nice conference. I won't say it's good to be here, but I've been here for a long time, but it's good to have everyone here and to discuss in person. That's really nice. And I'll be talking about a couple of papers with Sergio Guri in Argentina. Okay, this is complicated. Sergio Guri in Argentina, Davide Buffalini, and David Turk, who are here in the audience. And the third one that's hopefully to come out very soon. And the idea is to try to focus on some particular cases of microsites where we have an exact worksheet description, and to use it to compute as many things as we can. So this is the outline of the talk. Thankfully, David saved me some time by introducing JMAR geometries, which that's what I'll be using. So I'll just go briefly about the main parts or the main ingredients I'll be referring to along the talk, and then I'm gonna try to describe what the worksheet models are. These worksheet models have been introduced by Emil and Stefano Masai and David Turton. And the idea would be exactly to show how we can use this to construct the vertex operators in those models and to use them to actually compute a whole pretty large set of heavy light correlators, or what people have been calling heavy light correlators from the worksheet theory. And then I just conclude. So I don't need to motivate too much with this audience why we think that black holes are interesting, why we think that we know that they are out there, we can see them, we can probe them, we can know a lot of things about them now, even experimentally, which is very exciting. But they also push us to kind of understand more about the fundamentals of what we're doing when we try to describe gravity, and in particular quantum gravity. Because we need to know a microscopic origin for their entropy. We need to know if there is information loss or not. We need to know how the UV resolves the singularity, and we also need to know where there are physical horizon scale. So many of these questions, all of them are addressed in the context of the Fastball proposal, which is what largely what we're discussing in this conference. And for some of them, the answer is more precise. For some of them, it's more quantitative. But most of the information we get comes from using string theory and holography as techniques. So the idea, of course, is that we think of these black holes as some average description of a whole lot of an exponential number of microseconds, and a subset of which are well described within supergravity. They have no horizon, they are smooth, they look like the black hole for a distant observer, and they differ from it at the horizon scale. So given these geometries, these microsize geometries, we can think about probing them, and one way to probe them is to study the physics of probes in this context, in these geometries or backgrounds, and the different kind of interactions particles can have in the that particular states can have with the background here will tell us a lot. Will contain a lot of information about for example, what's the microscopic process behind, say, Hawking radiation, or whatever physics we want to extract in order to, for example, construct the observables that we would measure from here. So the main two techniques we use so far, or we have mostly used so far, are supergravity techniques, where we use wave equations and perturbation theory on top of these geometries when they are well described in supergravity, or ADS-CFT. ADS-CFT is mostly used in the sense of going into the IR region, which is well described in terms of a dual CFT. So the region has an asymptotic ADS3 boundary. That's well described within the CFT2, and within that CFT2 computes literally this set of heavy light correlators. So these are light insertions in the middle of heavy states, and we can go ahead and use the CFT2 on the boundary to try to compute those and compare to what we get, for example, from supergravity, or to try to extract more out of it. However, there are a couple of problems with this. First of all, we expect many of the microstate to be actually stringy, so not well described within supergravity. So that makes it difficult to use the first of these two techniques. And the second one is that most of the heavy light correlators will be non-protected quantities, meaning that, for example, if we want to cannot use the simplest model that we have for the holographic CFT, which is the symmetric product orbifold theory that Sean and David were talking about. And for many quantities, that would give a different answer from what you get in the actual microstate geometry or state at the point in moduli space where this background is defined. So having a worksheet description for this it's very important to try to address these two issues. Okay. So let me just give a very, very brief view of some of the things that David just said, and just those that are going to be important to me. And please interrupt me if you have any questions, of course. So I'm going to be focusing on a set of states that, as David said, are called the JMAR family of solutions, largely in terms of this paper, but also previous authors before for some particular case or subcases of it or subfamilies. And these have the following characteristics. They are microstates of asymptotically flat black holes in 5 dimensions. These are, in general, 3-charge systems, which we can view, for example, in the D1, D5P frame or in the NS5 F1P frame, which is the one I'll be using, obviously for obvious reasons, because I'm going to try to use the worksheet theory. They have a near horizon ADS3 region, which is well described within holography. And they are generically non-supersymmetric and with a macroscopic horizon. Of course, they include, as I said, they include a lot of previously known cases, BPS cases, and 2-charge cases in the geometry in this family of solutions, and those will be also included in what I'll be discussing. However, they have 2 drawbacks, which I want to be clear about. The main one is that even though these are microstates of these black holes in the grand canonical sense, they are not typical microstates. Okay, so we have to be careful about what kind of conclusions we get from the quantities we compute or what kind of interpretation we have. However, as David was saying, there's a sense in which there's a parameter. This parameter k is the same parameter k as in David's talk. It's about the orbifold structure of the vacuum, or it's about the word fractional in the fractional spectral flow on the boundary used to construct these states. And if this parameter k is taken to be larger and larger, then there is a sense in which these geometries approach more and more the physics of the black hole, in the sense that they in the diagram that David was showing, they approach this parabola. Okay. And the second drawback about these microstates in particular is that they have an ergo region, and they have an instability associated to that, as discussed originally in this paper, I think. But for what I'm going to say, this will absolutely not be important for a reason that will become clear in a second. So this is just to flash that in this paper here by Emil, David, and Stefano, you can look at all the fields defining these solutions. You have the metric, you have the B field, you have the consistency conditions telling you that these geometries are regular, etc., or they don't have horizons, they don't have closed time-like curves, etc. But I don't really care about all the details of this. All you need to know for kind of following the talk is these features here. So this is the idea of the geometry. There's an asymptotically flat region. Then if you go further into the infrared, so the whole geometry is defined by first of all by 3 charges, which I'll call the quantized charges, N1, N5, and P. Obviously, the number of fundamental strings, the number of NS5 branes, and the number of momentum units. And it's also defined by these parameters here, which are the asymptotic radius of the Y circle. And then S bar, and K, which define the angular momentum and the angular momenta and the orbifold structure at the origin of this geometry. And in terms of the holographic theory, they are associated to this fractional spectral flow. I'll be a bit more precise about that in a second. And so if you go a bit into the IR and you take the NS5 decoupling limit, you basically take everything that's up of this plane here. You take it to infinity. Okay, you decouple it, and that's important for us because the ergo region is part of that region that's decoupling. So you're sending it to infinity. So when you do that, these geometries, these backgrounds become stable. Okay, so then you have a region, this whole region here, which is asymptotically linear dilaton. Okay, and that's known to be holographically dual to what's called little string theory. This is the way you take these NS5 decoupling limits. You take the G string to 0 with the radius over G string fixed. And then you can take a further F1 decoupling limit, the ADS3 limits, where you go to the region which is well described in holography, in conventional holography, which is the ADS3 CFT2 regime. And you go this, which is downstairs here, and you go to this regime by taking this radius of this asymptotic radius of the Y circle fixed. You take it to be large, and then you take T and Y, which are going to appear in a second. So a time direction and this Y circle over this are Y to be fixed. We will focus on this, as I was saying, we focus on this region here. This whole region, including the asymptotically linear dilaton part, is the whole region that's going to be described by these worksheet models.
Sorry, what do you mean by T and Y fixed? They are just the coordinates there, and usually when you flow down, I think of them as ranging over all possible values. So I'm not sure what you mean by.
It's just I'll be clear in a second, but it's just about, so if you look at the metric and the fields written in terms of these T and Y coordinates and this RY radius, one way to quickly engineer the limit to this region is to take those two things fixed. Of course, it's like the you don't kill, like for example here you don't kill radius.
Prescaling them.
Yes. Exactly. Yes. Yes. So this is for the NS5 harmonic function, and this is for the F1. Okay. So as David was telling you, this whole state, this microstate have a well-known description in the holographic dual theory at the level of the IR of the geometry, the infrared of the geometry, and they are described in the language of the symmetric orbifold theory. They're described by this concept of fractional spectral flow. So just maybe one picture to clarify what this is. You basically take, here you have a lot of copies in your copies of your theory that are not coupled to each other. In principle, they are only coupled when by the fact that you're quotienting by this permutation group here. And what you do when you do fractional spectral flow is, first of all, you go to n over k copies of k twisted strands. So strands where you twist k copies of the theories together. You do that all the set of copies, all the full set of copies you have. You take those in groups of k. And then where you are in these k twisted vectors, you perform the usual spectral flow operation. And when you do that spectral flow operation, in terms of the covering, it's the usual spectral flow in terms of the covering space coordinate. You get to the states that are dual to the geometries I was describing. And these parameters k, s, and s bar that define the geometry are exactly what tells you how much spectral flow you need to do. Okay. Okay. So it was shown very recently, a couple of years ago, in a very nice series of papers, but that this geometry can actually be understood directly from the worksheet of strings. In terms of a gauge Quasimodo-Witten model, which is a coset theory where the target space is of this form. And the idea is that you start from a 12-dimensional geometry, which I will often call the upstairs geometry. The upstairs, well, I cannot move this hand correctly, but here. And you start from these 12 dimensions, and then you gauge away 2 of them in order to go back to the physical 10 dimensions of string theory. And why it's done here is that what you gauge are 2 chiral, both chiral and null currents in this case. Okay, So you combine, you take J3 and K3 here, which are the Cartan currents in SL2 and SU2, okay? And then you combine them with the T and Y derivatives of these extra T and Y directions here, and you gauge some linear combination of them on the right and some linear combination of them on the left, okay? And the fact that these currents are null is characterized, so I have in principle arbitrary coefficients here. So in order to get the J-Mart geometries, these coefficients are obviously related to, this is a mess. Okay, these coefficients S and K are obviously those that define the angular momentum and the Roby structure of the geometry. So they enter exactly which are the currents that you need to gauge. And the fact that this current is null is defined by imposing this condition here. Okay, so that condition tells you that both currents are null, and that's going to be important for the construction. And a little detail that's going to be important is that these parameters k plus and k minus, when I take the infrared limit of the geometry, so when I go to the ADS3 region, because I have an Ry multiplying the k there, that they are going to be large. Okay, when I go to the infrared, I take Ry to infinity, k is fixed, and so these parameters there are going to be large. And this is telling me that basically I go to the IR, I'm mostly gauging away the T and Y extra directions, and I'm getting back to some ADS3 cross S3, which is almost ADS3 cross S3. It has this orbifold structure and this extra large case transformations on top. So in our first paper last year, we showed that if you allow for any other coefficients in front of these currents, for this linear combination of currents, if you allow for any other coefficient, the most general coset model with this type of structure that you want, then the only such models that are consistent at the quantum level in the spectrum of the spectrum of the worldsheet theory is consistent. All of those are exactly the full set of the J-Mart geometries. Okay, so that's the first conclusion. The second conclusion is that the way this happens is that we can see very clearly how the conditions of having no horizon, that the geometry is regular, and that there are no closed time-like curves is exactly what gives a consistent worldsheet spectrum. And whenever you don't have those there, the worldsheet spectrum is inconsistent. Okay, and a third outtake from this analysis is that by showing, but because in this worldsheet language, the T duality is very simple because you just exchange these two guys basically. It's just yes.
So this coefficient is exactly by anomaly and BRST.
Well, if the currents are null, then there's no anomaly.
Yeah, right. That's the zero.
Yeah, and then BRST. Well,
I mean, I can put arbitrary coefficients.
Yeah, that's what I'm saying. So whenever you do that and you want to get a consistent quantum theory, so obviously through BRST quantization, then the only thing that survives are the J-Mart geometries. Okay, and we are able to compute a new set of NS5P solutions that non-BPS, which were not known because it was kind of difficult to take the limit in the correct way. But okay, these were the outcomes of the first project. Yes, just a short one. Yes, S plus and S minus are exactly S and S bar. So no, S plus is 2S plus 1, and S minus is 2S bar plus 1. And the reason why I need them to be odd, what I'm saying 2S plus 1, they are odd, and they are odd exactly because of what David was saying, that I always want to end up in the Raman sector of the theory. So in this language are odd in what there's a little one difference from what convention from what David was saying, but that guarantees that you always end up in this type of sector. Okay, any more questions? Yeah.
Irregularity in horizonness and consistency of the VS spectrum is that one-to-one? So do you know if you get a consistent worldsheet spectrum that you will have solutions which are regular without CTC on horizon?
Well, for all of this class of models, yes. Okay. I would like to think that there is more generally this type of relations are true, but obviously I don't have a proof for the whatever worldsheet theory you could come about. I would hope that this type of relations hold in general. Okay, so a little bit of an aside is that so these coset theories, you can think about them. They are gauge Wessel-Minowitz models, and if you fix the gauge, if you quickly by hand fix the gauge, you get into an action, a Lagrangian, which is the original Lagrangian plus this term here, okay, where this J and J bar are the current that I was gauging exactly. Well, I fix the gauge. So, for example, imagine I take the T and Y parts away. I set them to 0. So this is the combination of the SL2 and SU2 parts of the current that I was gauging, and I have a coefficient in front here, this sigma. So there are several comments to do about this. The first one is that this sigma tells you where the sources of the geometry are. Okay, so the zeros of these coefficients are important because that's where the, admittedly, depending on the frame, smeared sources will be. Okay, so even if I have a discrete array of an S5 brane, this sigma function will show you the singularity at the whole circle, or something like that. But more importantly, this matches well with the new story about the kind of TT bar deformations that people have been studying. In particular, the later idea of these single trace TT bar deformations put forward by Kutasov and collaborators, and by, in particular, Sumanshu here in various of the papers. And the idea is that instead of thinking that I have a full asymptotically flat geometry, or at least a full asymptotically linear dilaton geometry, and I go back to the IR and I get this, and I have these models, I can complementarily think about them as I start from the ADS3. Okay, I have a theory there, and then I do at the worksheet level, I make this deformation on the worksheet theory. Okay, and when I make this deformation, what this does is that it forces me to flow back into the UV, into the asymptotically linear dilaton theory. Okay, and the way it flows back is because when you look at what this does to the geometry, it effectively adds the 1 plus in the harmonic function of in the H1 harmonic function. And as I was saying, the holographic dual story to this is that you're taking your CFT2 and you're doing some sort of TT bar irrelevant deformation type single trace, and that's important. And that deformation of the CFT goes into the what would be the holographic dual of the full asymptotically linear dilaton thing, which is this non-local theory that we call litter string theory. Okay, so that's yes.
So is it obvious that what you're describing is the same of the Kutasov story? Because their geometries have horizons.
No, that depends on. So for the easiest setting of the Kutasov, well, he's the expert obviously, but the easiest setting of the Kutasov theory is just global ADS3, no horizons, no anything. Okay, and you do. So, but there's no horizon. I mean, you can turn on do the same when you have some temperature, and then you're gonna have a horizon, and there's the whole story there. Poincare. Okay. Right. Yeah, the current is different. Yes. No, I'm not saying it's exactly the same story. I'm saying TT bar type deformations. I'm trying to say that you can think about this in the same way. What exactly is the dictionary to that way of thinking? I mean, I could have some more precise comments if you want afterwards, but this is more qualitative at this level. And this, again, the last comment is that this, morally, I think the idea is that you have these JJ bar deformations, and then when you do them, you glue back this extra UV region, and you get something that's related to litter string theory. I think that's true in all of this, in all of this type of deformations, but we can discuss the details. No. Sorry, even? Yeah, but not on the on the worksheet level. It's not on the holographic CFT2. On the holographic CFT2, it's an irrelevant deformation. It's some type of combination of T and TT bar, JT bar, stuff like that. Okay, and the parameter in the deformation is exactly related to this RY, which I used to scale from the infrared to the UV. Okay, so how much am I doing on time? Okay. Okay, so we have this worksheet model. Very nice. It gives us we have an exact description of the geometry in terms of worksheet things. So let's actually go ahead and use it. Okay, let's actually quantize it. Let's actually use it to compute correlators exactly, which is kind of the natural thing to do at the worksheet level. Of course, there are other interesting things you can do. For example, again, Stefano, Emil, and David looked at the D-brain states, which help you resolve the individual sources, which you wouldn't see with just string probes, and this framework was very useful for that. But I try to go on the talk to direct myself to compute correlators in this worksheet theory. Okay. The idea is very simple. The idea is that if you look at the action at the path integral quantization, because of the fact that these currents I'm gauging are null and chiral, then what happens is that this gauge Wessel-Minowitten action, I can rewrite it by just a simple change of variables. I can rewrite it exactly as the original Wessel-Minowitten action in terms of gauge invariant variables. Okay, so these are not the same original variables, but in terms of these new variables, the Wessel-Minowitten action appears exactly in the same way, plus Gauss contributions. Okay, and that's nice because it tells me that when I go ahead and quantize the theory using BRST quantization, I get the usual T and G terms in the BRST quantization of worksheet strings, and then I get extra terms, which are this Cj and lambda and gamma lambda, which are just imposing gauge invariance on the vertex operators, right? They just impose that the vertex operators don't transform under the currents that I'm gauging, under fermionic partners. And the fact that this action here is the same as the original action formally tells me that all I need to do to construct the vertex operators is I need to take the vertex operators in the upstairs theory. Okay, so the SL2, the 12-dimensional theory, SL2, SU2, T and Y directions, and then the T4. Okay, I take the vertex operators there, and then all I need to do is impose some conditions relating their quantum numbers so that they are gauge invariant. But the vertex operator in the theory looks exactly the same. It's just that it looks exactly the same as in the 12-dimensional theory. It's just that the quantum numbers that you have are not independent of each other. Okay, but this is very nice because it tells me that whatever I knew about computing correlators in the upstairs theory, I can use to compute correlators in this coset model. Okay, and so in this way, we're going to build the vertex operators that are going to be dual to light state perturbations of these geometries in the IR, or to LC operators in the full linear dilatant geometry. So since I need to use the ingredients of the upstairs model, which are SL2R, SU2, and just free bosonic fermionic fields, then let me introduce just the basics of what I need to use. And the most important building block here, obviously, is going to be the Wessel-Minowitten model of SL2R, okay, of ADS3. So I just have a very short summary of the things I'm going to be needing. So this is how the algebra is defined. These are the type of states that you have. As you know, you have long string states and short string states. Okay, these long string states only make sense when you think about them as winding around the asymptotic boundary, with a non-zero amount of winding omega. Okay, and they have a little. They are defined by quantum numbers little j and little m, as you do in the usual SU2 theory. In this case, little j is a complex number. And then you have the short strings, which are states that are bound near the center of the ADS. And these states have a real value of j, and the values of m, which are the projections of this j in the z direction, can take specific values, which are plus minus j plus minus integrals. Okay, plus minus natural numbers. So this is the basic picture, and let me say that this sector here is the sector that includes all of the worldsheet duals of the chiral primaries of the dual CFT2. Okay, so if I think about, for example, the symmetric orbifold CFT2, I can compute a full set of chiral primary states. Okay, and when I look at the worldsheets here in ADS3, here I have a list of worldsheet vertex operators that correspond exactly to those states. Okay, and in the usual of ADS3, the correlators of the, for example, the point functions of chiral primary states are protected, and I can compute it. I can get the same result if I compute them on the worldsheet or if I compute on the symmetric orbifold theory. Okay, so I'm gonna the first thing I want to focus on seems trivial at first, which are the worldsheet 2-point functions. Okay, and so I need the SL2R worldsheet 2-point functions. These look like this. Okay, so you have some normalization function, and then you have a bunch of gamma functions here relating the projections. And then when you just as a comment is that when you go into the supersymmetric theory, you need to make combinations of bosonic and fermionic fields, which such that the overall spin, SL2R spin, this linear combination is well defined, and in particular for the chiral primary states. For example, you can take one of the where the spin of this linear combination is the spin of the bosonic guy -1. Okay, and so on to construct the full set of operators. However, if we want to compute local correlators on the worldsheet, okay, we need to define local correlators we need to define what the local coordinate on the boundary is from the worldsheet point of view, and this we need to go to so-called spaces, and in the so-called X spaces, this X is going to be the coordinate on exactly the coordinate on the boundary, and in these spaces, these generators act as the usual differential operators, and the 2-point functions are just the usual. This is the worldsheet coordinate 2-point function, and this is the boundary coordinate 2-point function, and they take the usual form. Okay. So just try to remember the fact that X is the local coordinate on the boundary on the holographic FT, and it will be important for us. And it's really important, as was highlighted, for example, in the recent papers by Andrea and Lawrence Eberhard, that it's really important to think in terms of this X basis when you compute correlators, as opposed to the M basis, the correlators of the projections, which correspond to correlators of modes of the operators and not local operators in the holographic theory. So as I was saying, there is a whole set of chiral primaries in the symmetric orbifold language. You have, for each twist sector, you have 3 chiral primaries. Okay, one has weight, if the twist is n, one has a weight n-1/2, the other n/2, and the other n+1/2. And this set of chiral primaries are exactly mapped to the worldsheet theory in ADS3. They correspond to states. The families correspond to states which are polarized. NS states polarized along the ADS3, NS states polarized along the SU2, and Ramon states. Okay, so the 3 families are there. And so we will be looking at local correlators, and I just wanted to highlight this nice series of papers. I already mentioned Andrea and Eberhard. There's also recent papers by Emil and collaborators, and also Eberhard, on what the worldsheet dual at the point where you actually the holographic dual of the exact worldsheet theory is, and it's kind of a conjecture to be kind of a different symmetric orbifold with some twist-2 deformation on top of it, which was already mentioned, for example, in Sean's talk. And then there's also a nice set of papers by these people here working on the particular case where the level of the ADS3 algebra is 1. And that's nice because it highlights the relation between these correlators and covering maps in the boundary theory. Okay. So let's go back to our coset models, and I want to construct the worldsheet vertex operators in our coset models. Again, let's remember that these are the worldsheet models for the J-Mart geometries, okay, for these microstates. So I want to construct the operators, and I just need to impose, as I told you, the Virasoro constraints and the gauge constraints. Okay, so I take this thing, which is an upstairs, kind of an upstairs vertex operator. So the SL2 guy, the SU2 guy, and the exponentials for the free fields. And then I need to impose this thing, which is the Virasoro constraint, and then this thing, which is the gauge constraint. Okay, so the gauge constraint obviously cares about the charges with respect to J3, K3, and etc. And the Virasoro constraint cares about the weights, and because of the fact that you have the extra t and y coordinates, you have these extra e squared and py squared terms as compared to the usual ADS3 story. However, one thing that you have to take into when you construct these states is that, as Rodolfo, as I was answering to Rodolfo, the conformal symmetries, the symmetries of ADS3 and the symmetries of SU2 are broken by the gauging because some of their operators do not commute with the BRST charts. They do not commute with the gauge invariance condition. Okay, and so that's one way to say that the symmetries are broken, and that's one way to say that when you construct these states, you want states that are not necessarily going to have definite spin under the upstairs SL2 and definite spin under the upstairs SU2. And that's, you need to relax that condition. And when you do, it's very direct to find that you need to construct this type of vertex operators. These are the first type of vertex operators that on these worksheet theories are equal to the chiral primary perturbations of this to perturbing these Riemann geometries by light states, which correspond to the chiral primary states of the dual CFT. And all you get is something very similar to what you get in ADS3. You have this extra exponential here, and also in this linear combination of fermions and bosons, you need to add extra pieces, and these extra pieces you need to add are necessary for satisfying two conditions, and their coefficients look like this. So that they depend exactly on what you're gauging. Okay, they depend on these parameters k plus mu and k plus mu here that tell you exactly which are the currents you're gauging. So which of the J-mar geometries you're looking at. And also this modified Virasoro condition leads to a value for J, for example, which is different from what it used to be in pure ADS3 cross S3. Okay, fine. So we have this type of operators. We in the paper we do for the NS state, for all of the set of states that are dual to this full to the primary operators. Okay? And so we want to compute the correlators. But then computing the correlators is a very simple thing. These are the same operators before. And if I want to compute correlators, every of correlator there's SL2R correlator, and upstairs SU2 correlator, and upstairs just exponential correlators, free field correlators, and all of those look exactly the same as they would if I was doing no gauging. It's just that when I look at the results, the quantum numbers are not independent of each other. Okay? So this looks very simple, and this is a way to define the worksheet correlators in general. And these worksheet correlators, since the worksheet theory itself encodes the heavy state I'm working on, these worksheet correlators are directly heavy light correlators in spacetime. Okay, because the information about the heavy state is already in the worksheet theory itself. So vacuum correlators in the worksheet theory correspond exactly to heavy light correlators in spacetime. Okay. Any questions about that? Okay. So in particular, this is a way to define, is encode the dynamics and the probes of this family of microstates. This is a way to define heavy light correlators, for example, in little string theory, which is kind of more difficult to discuss. And they also, this type of states that we just constructed, encode the way that a state flows when you start in the IR and you go into this irrelevant deformation. This flow is characterized by this type of extra coefficients in the new terms here. Okay. So in the remainder of the talk, I'm going to focus only on the infrared part of the geometry, which is the part that I can relate very directly with ADS3 CFT2 duality to heavy light correlators on the holographic CFT. Okay. Great. So so what happens to this? As I was saying, everything looks very similar to as if we were doing no gauging, right? It looks very similar to ADS3, and in particular the Virasoro condition just reduces, since I'm scaling the energies, the T and Y in the way that Guillaume was asking. This extra contribution to the Virasoro condition just vanishes in the infrared limit, okay? Because this E and R scale squared, scale like 1/RY squared. And so the Virasoro condition just reduces to the usual Virasoro condition in ADS3, okay? So the question is, these correlators look really very simple, okay, in the M basis. So should I expect anything different to the usual story? And the question is yes. And this was showed, the answer is yes. And this was showed by Rodolfo and collaborators. But for example, they from a completely different perspective, they looked at the supergravity. They computed the heavy light correlator in one of these, in a BPS subset of backgrounds in this context. And they did it in a completely different way, as I'm showing here, and they get this result. Okay, so this result is clearly not the ADS3 correlator. Okay, it's clearly very different from it. And from what I was saying so far, it's not clear how to get it from the worldsheet theory, because everything looks very similar to ADS3. And the answer to this is that what we just constructed are operators in the what is very easy to construct and what is natural from the gauging is to construct operators in the M basis. And the tricky part is to redefine what the local coordinate on the boundary means. Is to recombine in some way, which at the level of 2-point functions is just enough to think about it this way. The part is to recombine the M basis correlator into a local correlator on the boundary, right? So to sum over all the possible modes, because what are the modes in this case? Which mode out is non-trivial, and that's non-trivial, and I can show it in this example. So if you take the result in the paper I was just showing, and you just rewrite it in terms of a series, okay, you can rewrite it in this way, but the exponents of the x's here are very different. First of all, they are fractional, okay? They take values in z over k. There's a k here, and this k is the orbifold parameter. And second of all, you have an n and n bar here, but you do not sum over all of the possible values. You only sum over values satisfying this mod k constraint here. Okay, so if you take this power series and only sum over these values here with this constraint, you get the original result. Okay, and that's true for all of this BPS geometry. Okay, so the question is, how do I see this from the worldsheet? And from the worldsheet, it's very clear. I told you that the Virasoro condition just reduces to the usual Virasoro condition in the ADS3, but the gauge constraint is important. The gauge constraint does not, it remains a finite non-trivial condition in the ADS3 region. And it looks like this. And it tells me that I have the upstairs ADS3 modes, which I call M and M bar. And then I have the T and Y, let's call them modes, combinations of energy and momentum in the T and Y directions, which I combine in these combinations here, which are the energy and the momentum again in T and Y. And this relation between these two things, gauge invariant, imposes that there is a relation between the two, which is mediated by the angular momentum of the geometry and also this parameter k here. Okay? And so this sum that I was just saying is exactly the sum over all the possible values of these my guys in terms of the usual M and M bar ADS3 modes. Okay, so this is a way to define exactly the result from Rodolfo's paper in terms of the worldsheet theory. What all you're doing is you're taking the almost trivial M basis 2-point function and you're summing them with these powers of x, but only over the values of my here, which are allowed by Genji variance in the coset theory. Okay. Okay, and there is a very nice simplification here, which is that this power series has no non-trivial coefficients. All the coefficients are 1. And that's only true because I'm looking at the simplest case, which is the weight 1/2 operator chiral primary in the dual theory. Okay, if I go away from weight 1/2, I'll have here a set of coefficients which are going to be the gamma functions appearing in the ADS3 2-point function. Okay, so these gamma functions will combine to give me what originally was the slightly more complicated power series of 1 over 1 minus x to some power which is not 2, which is 2h. Okay, so these are the coefficients of that series expansion. Right, so let's try to move past, in the last part of the talk, let's try to move past this specific set of examples, and let's try to, first of all, go to the full set of J-Mart geometries, and second of all, let's go to the full set of chiral primary operators. Okay, let's go to the full set. I'm not choosing any particular h, any particular weight. I'm letting it be general, and I'm not choosing any particular J-Mart geometry. So this is completely general in that sense. And so what you see is that one efficient way to impose, yes, 15, okay. One efficient way to impose the gauge constraint is to insert into this sum this type of Kronecker delta symbols summed over values of k. So this is just a nice way to impose these conditions here, right? To say which are the values that are for the MYs. And when you do that, you can rewrite it in terms of these phases here. And you can see that each of these phases e to the 2 pi I r times something which is an integer which lives in z over k. Okay, all of these phases here combine with the original powers of x here, and they combine in such a way that in the end you're summing over all of the kth roots of the original insertion point. Okay, and so you can just use this language, compute the full set of heavy, light 2-point functions in the full J-Mart family for arbitrary chiral primary light insertions, and they look very simple. They look like, so they give me, so again, this is a worksheet computation. It's not, the language is maybe slightly misleading, but this is a worksheet computation, and it should not be confused with the symmetric orbifold computation. You want to compute the 2-point function of 2 light insertions in whichever J-Mart background you choose, and what you have to do is you have to take the vacuum 2-point function, which is just this u1 minus u2 to the 4h. Okay, you insert some extra powers of u1, u2 here. These extra powers are defined in this way. And then instead of using x1 and x2, which are the insertion points, you use u1 and u2, which are the kth roots of those insertion points. Okay, and then when you have those insertion points, when you have those kth roots, you sum over all the possible kth roots. Okay, and this here is a very compact way of writing any heavy, light 2-point function, again, for any chiral primary light insertion in any of the J-Mart. And there are several things to notice here. So first of all, these extra powers that appear here are interesting. They have a twofold meaning. First of all, they have an h times 1 minus k factor, and that's giving you the Jacobian for going from the physical space to the k-fold covering space. Okay, and then you have this extra s times m prime factor, which is basically angular momentum of the background times r charge of the operator, which is just the usual way in which chiral primaries transform under boundary spectral flow. So spectral flow in the holographic theory, or fractional spectral flow in this case. So all of these results are exact in alpha prime. All of these results work for any J-Mart background, any chiral primary, and it also, as Andrea was asking me the other day, everything I've done here can be done for the spectrally flowed cases. Okay, so not everything can easily be generalized, and the message here is that even when you have spectral flows, and this is going to be true for higher point functions, not only 2-point functions. You take the vacuum 2-point function, and then you do this procedure. You add some factors, and you sum over the roots of the insertion points. No, because the whole point is that this is not Lunin-Mathur method. The covering map I'm using here is only the covering map defined by the heavy state. It's not defined by all the states in the correlator. Okay, and that's a simplification. I have a couple more comments about why that happens. And for example, one of the consequences of this formula is that you can use it to reproduce the Hawking rotation rate for any of the Chaimard geometries that was computed in this paper by David and Bidisha and collaborators. And from special cases of this function, you can go and compute the Hawking radiation rate, and then matches exactly the computation from the symmetrical for CFT. And so, but as Andrea was asking me the other day, and as I was saying at the beginning, I would like to, in the last 5 minutes of the talk, I would like to go beyond 2-point functions in the worldsheet, so beyond heavy light correlators. I want to be able to insert more light insertions into my correlator, and for that I definitely need to work on the local X basis and not on the M basis. Okay, so I want to stop thinking about sums over modes. I want to think directly in the X basis, and for that I just noticed that the whole procedure we did was not really a procedure on the full correlator. It was a procedure which is operator by operator. Okay, so I can directly translate the whole non-trivial thing, which is the gauge invariance condition, and translate this type of gauge invariance condition, translate it directly to the X basis. Okay, and the idea is the following: this my here is the physical mode, if you want, and it's picked up in the local basis by this differential operator. And this auxiliary M, which is only the upstairs ADS3 mode, not the physical one, is picked up by a similar differential operator where I allow for some extra shifts, which in principle I don't know what it is. Okay, and then I just noticed that if I pick this extra shift to be exactly this powers here on the extra things that I need to put in the correlator before summing over the roots, I notice that the gauge invariance condition just becomes the condition that this auxiliary variable u to the k is x. Okay, because all of the other terms cancel if I pick the correct beta. Okay, so the gauge invariance condition directly in the X basis is telling me that what I need to do to define gauge invariant operators is I need to define them in this way. I just take the usual construction in the ADS3, then I just evaluate them at the kth roots of the physical insertion points. Then I multiply by u to the beta and u bar to the beta bar, and then I sum over all the possible roots. Okay, and this is operator by operator, and hence, since it's operator by operator, I can do it in any arbitrary correlator. Okay, and so I'm gonna let me skip and come back. Maybe I'm gonna get an arbitrary formula for arbitrary light insertions in these backgrounds, which is just a heavy light correlator with an arbitrary number of light insertions here, where if you give me the vacuum correlator, I give you the heavy light correlator. Okay, so if you give me the vacuum correlator, Andrea would give me, I follow this procedure, I evaluate it at the kth roots, I put these factors, I sum over the roots, and I give you the heavy light correlator. Okay, so this is true for arbitrary light insertions. And then you would say, okay, this sounds nice. This sounds a bit nice. Okay, it sounds too general to work correctly. So I have 2 comments to say why it should work. And moreover, I have 2 comments to say why it actually matches symmetric orbifold results. Okay, so first of all, think about light insertions in the untwisted sectors. Have 5 minutes? Yeah. Okay, think about just light insertions in the untwisted sector. Okay, if I have operators built in the untwisted sector, I build them in this way. I just sum over the copies. But since I'm working in a k-twisted sector, I can construct the fractional modes of this operator. Okay, just as in the Lunin-Mathur papers, and I construct the fractional modes in this way. And so I can invert this formula, and for each copy, I can construct the operator as the operator in each copy as summing over the fractional modes with this power, with this phase here. And then when I sum over all the copies, I get exactly the sum over phases, which I was showing on the worksheet. Okay, and so for untwisted operators, it's absolutely clear that this construction of a gauge invariant operator in this way is exactly analogous to what you would do in the symmetric product orbifold theory. Okay, there's absolutely no difference. The way you construct these operators to go to to work in the k-twisted sector is exactly the same type of sum over kth roots of the physical insertion points. Okay, so in this sense, for example, in the first example I showed, it's not surprising that the result matches that in Rodolfo's paper because those h = 1/2 guys were untwisted sector chiral primaries. Okay, so you would tell me, okay, but if this works so nicely in the untwisted sector, then probably it works down in the twisted sector, and that's where I should see the difference with the theory at the supergravity point and at the symmetric orbifold point. Okay, and so my last comment on that is that we can actually check what happens when the case in the case of two insertions which are twist 2. Okay, because in the case where insertions are twist 2, this type of correlator was actually computed in a recent paper by Lima and collaborators. Okay, in a recent series of papers, and they actually computed this in the symmetric orbifold using the covering map method. Okay, the Lunin-Mathur method, which is completely different from what I'm doing here. And they computed it, and they show that, so in principle, because you have a twist 2 guy and you have a bunch of, let's say, twist k Ramon ground states in your correlator, you have a lot of possible contractions between them, and you have a lot of possible structures that could contribute to this correlator. However, they show that when you go to large n, there is only one type of contribution that survives, and that type of contribution that survives is not a function in the covering space. It's actually a 6-point function in the covering space. Okay? Because if these guys are twist 2, in order to have, you count the genus of the corresponding correlator with the Riemann-Horowitz formula, and you need to involve 2 copies of the full n/k copies of the heavy state on each side. Okay, and they compute this 6-point function using the covering space method, as I was saying. The map, as Sean was telling us the other day, the map for these kind of things, when you have a 6-point function, becomes much more complicated than usual than 4-point functions. But what you can show is that even if the map is complicated, there's a nice relation of this form between what I would call the physical space cross ratio and the covering space cross ratio. Okay, so you get this relation here. You can compute each of these guys exactly here, like this. These are the blocks, the results of this type of correlators in the covering space. And then you need to go back to physical space and sum over all pre-images of this map. Okay, which is, again, it's not x equals u to the k. Different covering map. The different map and the pre-images are different things. And when you actually use these correlators and sum over all such pre-images, you get a result which matches our formula from the worksheet exactly. Okay, so this result looks exactly as what I was showing here, like this, when you look at the twist guy. Okay, so even in the twist 2 sector, it seems to work. And then finally, you could tell me, okay, this seems nice, but it may be only a property of two light insertions, so a property of worldsheet 2-point functions, and then it becomes more complicated. And then we actually went, and as Davide will tell you in detail next week, we actually went and computed the first heavy light heavy correlator in the microstate geometry. We did it in the simplest possible case, which is where the light guys have weights 1/2, 1/2, and 1, and we did it using similar techniques as you guys in the appendix of your paper. We compute that in the symmetric orbifold theory exactly, and then we compare that formula to the formula that you get from this more general formula for arbitrary light insertions, in this case 3. And you can show again that the result matches exactly. Okay? So we expect this formula to hold for, again, arbitrary J-Mart size, arbitrary number of light insertions in the chiral primary multiplets. Okay. So if there are no questions, let me conclude. So briefly go over what we did. We constructed the vertex operators in the full J-Mart coset models built by Emil and David and Stefano. We computed all heavy light correlators in such backgrounds in terms of the local coordinate on the boundary. They have a very nice and simple structure. The method, for example, is much more simple to what you do in the symmetric orbifold theory when you look at this, for example, twist 2 case, which quickly becomes a mess. And these papers by this Lima group and so on are very nice, but they are very long and they contain a lot of computations from one result to the other. And also, and this is important, we found for all of such quantities, we found an exact matching with the symmetric orbifold CFT. And this is very non-trivial because most of these geometries are non-BPS. Okay? And so in principle, they are not covered by the usual non-renormalization theorems, also because these are 4 or 5 functions and not 2 and 3-point functions in the holographic CFT. And we don't yet have this is not the first time that type of matching of kind of non-expected matching at the beginning happens. For example, when I was telling you about the Hawking radiation rates for these geometries which were computed, which are kind of a special limit of one of functions, David and collaborators show that the result from the supergravity side and from the CFT and from the symmetric orbifold CFT were the same. And I guess the only thing I have to say about that so far is that in some way, these type of things are, even if they are non-BPS, they are protected by this fractional flow we use to build these geometries. And then what we would like to do, there are a lot of things we would like to do with this. We would like to use to go beyond the Hawking radiation and to compute a lot of maybe observable signatures. Yes, I'm finishing. And then there are things we can use from this to learn about the dual CFT. We can use to think about the flow of this size and not restrict to the IR of the geometry and look at the full litter sink theory. And in this case, there's only one nice comment, is that the way in which we build this boundary coordinate kind of breaks down when you go to the UV, and it should break down because litter sink theory is non-local. Okay, so that's also expected. That's all. Thank you.
Questions for Nicola? Yeah, just take that.
It's about the light, heavy correlator. So
yeah.
First of all, why is this the Penrose process? Can you?
No, I'm just saying that you can think about the Penrose process. I'm referring to a specific paper here, I think. I didn't put, okay. Yeah, but the idea is that you can think about it as some particular limit of one particle interacting with the geometry and one going out and one going in.
Okay.
So yeah.
Okay. And for the calculation, I didn't understand. So you have a way to compute all the light operators, even for light,
all those that are well, okay. I have a way to, let me show the formula. I have a way to compute it in terms of the vacuum correlator. So, for example, if the vacuum correlator, if you go at 4 light insertions, then we don't know exactly the 4 light insertions correlator in pure ADS3. You would need that information. So whatever information you have there, you translate it to the heavy light.
So for the but the 4 light, don't you have it from the papers by Stefano and Rodolfo? I mean, there are some 4 light.
But those cases are not for Gemar geometries, as far as I know.
I see. No, but you said 4 light insertions for ADS.
Ah, yes, for ADS. Yeah. So okay.
So I think Stefano and Rodolfo, they computed this 4 light. I mean, by taking these funny limits. I mean, the funny derivative of, like, 2 light to heavy, they computed 4 light ones.
Right, so we don't have this exactly in the worksheets here.
Oh, and you need this exactly in the worksheet. But can't you use the supergravity result there to get the supergravity?
Yes, probably you can. It's something I haven't discussed with Rodolfo. I've also talked with Hinek a bit, which is not here, but worked on ADS3 ambitus. There is something it's in the plans of doing at some point.
Oh, okay.
Good.
But it works. It can be done. Okay, this is really cool. Okay.
Well, I think earlier discussed in a meeting, there is a one 6-point function you can compute, which is basically take a half, a half, a half, one half. So I think in that case, you would use this result. You take everything to be PQRS, you take it to be everything 1/2. You just insert in this formula, and you get something which I think depends on D functions. In this case, of course, the 4-point function is not protected in general. So you then compute it on the orbifold CFT. I think it's doable. You compute it in the same method that they have in the appendix, in the row basis. Then you can actually see the mismatch. But this mismatch is not about the formula here, the dressing factor, but it's about the vacuum correlator.
Right. So what David is saying is that whenever this vacuum thing is protected, so it's the same in the symmetrical for CFT and in the worksheet or supergravity or whatever, then I expect that this thing will also be protected. But whenever this one is not, then this result in the heavy effect light will be different at the supergravity point than at the symmetrical orbifold point.
Other questions? Yes.
Cool. There might be an explanation of why these things is also protected. So usually, when you just have ADS3, the covering space variable of the symmetric orbifold gives you the worksheet answer in the bulk. And here, essentially, the difference is that you have to undo the ZK. So essentially, your U variables undo the ZK orbifold. So the covering space of the symmetric orbifold corresponds to the ZK covering space of the worksheet.
But that's right? Only at k equals 1 or in general?
I don't know. I mean, this is just an interpretation of how it would work. I think that's why your covering map, I mean, this U to X map never changes if you change W, because it's the covering map of the ZK orbifold you have in the worksheet, essentially.
Yes.
I don't know.
I think so.
Is that the interpretation I should think of?
Yes.
That's essentially the question.
I would say that's exactly correct when the light operator is untwisted, because then the holographic CFT covering map is exactly the same, just U to the K. Where it becomes highly non-trivial is when the light operator is also twisted, because then the lunar Mathur covering map is much more complicated than this.
Because, I mean, in the dual, you are undoing an SN orbit, and in the bulk, you are and if it was ADS3, you would be done. But in this more complicated geometry, in the bulk, you are undoing the ZK orbifold, not the SN orbifold. So it's right that in the dual, it depends on the spectral flow of the individual parameters. But in the bulk, your geometry is always ZK independently of the spectral flow of the individual vertex operators. Yeah. So I think that should essentially explain why it works also for generic spectral flow, no?
I think
is this the interpretation? Right. Yes. I don't know. It's just an intuition at this level, but
I think it's exactly right. The intuition. I would love to be able to write down the real non-real renormalization theorem for these guys. I don't know exactly how to. There was some some comments in one of your follow-up papers, I think, or who was it? Galliani or no, okay. But I don't know the precise theorem. I think the intuition is exactly right. Yes.
You can understand any orbifold with the covering map method of Lunin-Mathur. They applied for SN, but you can do for any orbifold.
Yes.
And essentially, I think your prescription is undoing the ZK.
Yes, but the fact that it's in the K-twisted covering space in the symmetric orbifold description, and that it's non-trivial. That's exactly the same thing that the ZK at the supergravity point. I mean, apparently it is, but it's not obvious.
Agree. The way I like to think about it is that this is a covering map for the space-time, like in the bulk.
Yeah.
Rather than, it's like rather than the Lunin-Mathur covering map of the holographic surface.
Yes.
And then I think this is the right interpretation.
Yeah. Thank you.
Anyway, it would be very. I mean, I don't know if there's something exactly non-trivial to compute, but it would be nice to understand and to see very directly in terms of in this model how all of these spectral flow selection rules work, and they should work exactly in the same way for the light guy. Yeah.
Another possible thing to maybe is it on now? Okay.
Yeah.
So maybe another speculation is that if you look at this addressing factor in front of the vacuum correlator, maybe it commutes with some like non-renormalization theorem that are already present for the vacuum correlator. So maybe another possibility is that if you apply the same reasoning, so the paper by Baggio and collaborators is that if you apply the same thing, then maybe you should get the same answer, possibly, but just a speculation, another possibility. Then okay, but then we can see in different ways. It's nothing.
Is there other questions?